What if a single equation could unlock the deepest secrets of the universe? Imagine a theory so powerful it could explain everything, from the tiniest quarks to the vast expansion of galaxies, from the pull of gravity to the spark of electricity. It sounds like something straight out of science fiction, but this is the real, thrilling pursuit behind the theory of everything. For centuries, scientists have dreamed of unifying the four fundamental forces of nature: gravity, electromagnetism, and the strong and weak nuclear forces into one elegant framework. And today, that dream is closer than ever to becoming reality. Think about it. Right now, our understanding of the universe is split between two towering pillars of physics. On one side, Einstein's theory of general relativity paints a breathtaking picture of space, time, and gravity guiding planets and bending starlight. On the other, quantum mechanics reveals the bizarre, probabilistic dance of particles at the smallest scales. But here's the catch: these two theories don't just disagree, they seem to operate in completely different languages. It's like having two maps of the same city that refuse to line up. This isn't just a scientific inconvenience, it's a gaping hole in our comprehension of reality itself. That's where the theory of everything comes in, a grand vision to bridge these worlds, to find the missing piece that ties it all together. So why should you care? Because this isn't just about equations scribbled on a chalkboard. A theory of everything would reshape our understanding of existence, answering questions that have haunted humanity for millennia. How did the universe begin? What lies beyond the edge of a black hole? Are there hidden dimensions woven into the fabric of space? The quest for this theory is more than a scientific endeavor. It's a journey into the unknown, a story of human curiosity pushing against the limits of what we know. And in this video, we're diving headfirst into that story. We'll explore the cutting-edge ideas, the brilliant minds chasing this holy grail of physics, and the mind-bending possibilities that could emerge if they succeed. Buckle up, because we're about to take a ride to the frontier of knowledge, where the mysteries of the universe are waiting to be unraveled. To grasp the enormity of a theory of everything, we first need to meet the four fundamental forces that shape our universe. Picture them as the invisible architects of reality, each with its own unique personality and domain. First, there's gravity, the most familiar yet strangely the weakest of the bunch. It's the cosmic glue that holds planets in orbit, binds galaxies together, and keeps your feet firmly on the ground. But here's the twist: while gravity dominates the grand scale of the cosmos, its influence vanishes in the quantum realm like a fading whisper in a storm. Then comes electromagnetism, the force that lights up our world literally. Think of it as nature's electric handshake, governing everything from the spark in your nerves to the glow of distant stars. It's the reason atoms stick together to form molecules, and why your refrigerator magnet won't slide off the door. Unlike gravity, electromagnetism plays nice with quantum mechanics, but it still refuses to reconcile with Einstein's vision of curved spacetime. Now enter the strong nuclear force, the ultimate atomic bodyguard. Locked inside the nucleus of every atom, it's 100 times stronger than electromagnetism, overpowering the repulsion between positively charged protons. Without it, atoms would fly apart, and the universe as we know it would dissolve into chaos. Yet, this force has the shortest range, vanishing beyond the width of a single proton. Finally, there's the weak nuclear force, the shyest and most elusive of the four. It's the behind-the-scenes maestro of radioactive decay, quietly transforming neutrons into protons and fueling the fiery hearts of stars. Without it, the sun wouldn't shine, and heavy elements like gold and uranium would never exist. These four forces are like the rules of a vast cosmic game, each dictating how matter interacts at different scales. But here's the puzzle: why do they behave so differently? Gravity tugs gently across light years, while the strong force flexes its muscles only in atomic back alleys. Electromagnetism and the weak force occasionally team up, hinting at a deeper connection. Unifying them isn't just about stitching equations together, it's about uncovering the hidden symphony beneath the noise. The dream of unifying nature's forces didn't begin with modern physics, it's a story centuries in the making. Rewind to the late 1600s when Isaac Newton watched an apple fall and saw more than just fruit dropping to the ground. He saw a hidden thread pulling the moon toward Earth and planets toward the sun. His law of universal gravitation was the first great unification, revealing that the same force governing everyday objects also ruled the cosmos. But Newton's gravity stood alone, a solitary giant with no companions. Fast forward to the 1800s, and James Clerk Maxwell wove another thread into the tapestry. His equations showed that electricity and magnetism weren't separate phenomena but two faces of a single force, electromagnetism. Suddenly, light itself was revealed as an electromagnetic wave, and the universe made a little more sense. Then came Einstein. While most know him for relativity, few realize he spent the last 30 years of his life obsessed with a far grander quest, unifying gravity and electromagnetism into a single, unified field theory. To him, the universe's forces were like fragments of a shattered mirror, each reflecting a partial truth. He believed there had to be a deeper, harmonious framework hidden beneath. But the cosmos proved stubborn. Einstein's notebooks from the 1920s and 30s are filled with desperate scribbles, equations scratched out, and margins littered with question marks. He'd reunite the forces mathematically, only for the solution to crumble under closer scrutiny. What made it worse? The rise of quantum mechanics, which Einstein famously resisted. He couldn't accept that nature played dice, calling quantum theory incomplete. Yet, while he wrestled with unification, quantum physicists were uncovering the strong and weak nuclear forces, adding two more puzzle pieces to the mix. Einstein's struggle wasn't just scientific, it was deeply personal. In one poignant letter, he wrote, "I have become a lonely old man, known for wearing no socks and for failing at the one thing that mattered most." His contemporaries, like Niels Bohr, urged him to embrace quantum theory's weirdness, but Einstein refused. To him, the universe had to be elegant, deterministic. That tension between gravity's cosmic curvature and quantum mechanics' probabilistic frenzy became the defining rift of 20th century physics. And yet, Einstein's failures planted seeds for the future. His later work on general relativity indirectly inspired string theory, while his insistence on unification became a rallying cry for generations of physicists. The takeaway: even wrong turns in science like the path forward. Newton unified heaven and earth with gravity. Maxwell merged electricity and magnetism into a single force. Einstein's quest, though unfinished, showed that the universe's secrets might not lie in isolated theories but in the spaces between them. That's the legacy we're still building on today. Picture the universe as a grand stage with two lead actors who refuse to follow the same script. On one side, quantum mechanics delivers a frenetic, unpredictable performance, a world where particles pop in and out of existence, where a single electron can be in two places at once, and where reality itself hinges on probability. On the other side, general relativity glides across the stage with regal precision, painting spacetime as a smooth, curving fabric where gravity isn't just a force but the very geometry of the cosmos. At first glance, these two theories seem to belong to entirely different plays, and that's precisely the problem. Zoom into the quantum realm and the rules get weird. Here, particles don't just move, they flicker between states, entangled across distances in ways Einstein famously called spooky. The math behind this is flawless, predicting everything from the behavior of atoms to the inner workings of your smartphone's microchips. But try applying quantum rules to gravity, and the equations explode into nonsense. The quantum world thrives on uncertainty, yet gravity, as described by general relativity, is all about precise, deterministic curves in spacetime. It's like trying to fit a square peg into a black hole, literally. Now pull back to the cosmic scale. General relativity shines when describing the dance of galaxies or the warping of light around massive stars. But peek inside a black hole's heart or rewind to the universe's first split second, and relativity's equations break down. Why? Because at those extremes, the quantum world's chaos can't be ignored. Space and time themselves should start behaving like frothing quantum foam, but relativity has no language for that. The conflict isn't just academic, it's a glaring blind spot. Take a black hole's edge, where an astronaut falling in would be stretched like spaghetti by relativity's tides, while quantum theory insists Hawking radiation is slowly evaporating the hole from the outside. Both can't be fully right, or consider the Big Bang. Relativity paints it as a single, infinitely dense point, but without quantum gravity, we've got no idea what actually sparked the universe into being. This isn't merely a clash of theories, it's a battle for reality's rulebook. Unifying them would require something radical, a framework where gravity gets a quantum makeover, or where quantum particles learn to waltz to relativity's rhythm. Until then, the universe keeps its deepest secrets locked behind two doors, each with a different key, and the theory of everything, it's the master key we're still forging. String theory whispers an audacious idea. What if the universe's tiniest building blocks aren't dots but loops? Imagine every particle, from the quarks in your bones to the photons in your eyes, as microscopic strings vibrating at different frequencies. A guitar's strings produce distinct notes. Cosmic strings hum the symphony of reality itself. This isn't just poetic, it's a radical rewrite of physics' rulebook. Unlike the jagged clash between quantum mechanics and relativity, string theory offers a smooth harmony. Here's how: those vibrating strings don't just create particles. They are the particles, with their dance dictating whether they'll act as gravity carrying gravitons or light spewing electrons. One mathematical framework, four forces unified, but elegance comes with quirks. For the equations to balance, strings need room to wiggle, lots of it. Our familiar 3 dimensions won't cut it. String theory demands at least 6 more, curled up smaller than an atom's core. Picture a garden hose from afar. It looks one-dimensional, but zoom in and you see its circular surface. Extra dimensions could hide like that, shaping the universe's deepest laws without us noticing. Then there's the catch. No experiment has yet detected these strings or dimensions. They're trillions of times tinier than anything our colliders can probe. Critics call it a theory of anything, flexible enough to fit any observation but impossible to disprove. Yet the allure is undeniable. String theory gave physicists their first concrete hint that gravity and quantum forces might shake hands. It birthed mind-bending concepts like brains' higher-dimensional membranes where entire universes could float. Pop culture latched on too, from Brian Greene's The Elegant Universe to Interstellar's Tesseract. Even its variants, like M-theory, weave 11 dimensions into a single mathematical tapestry. But until those strings leave fingerprints in a lab, the theory remains a breathtaking what if a bridge between worlds, built on equations waiting for reality to catch up. If string theory is the symphony, then M-theory might be the conductor's grand score, a bold extension revealing hidden movements in the cosmic orchestra. Building on string theory's tiny vibrating loops, M-theory unleashes an even wilder proposition. The universe isn't just dancing to the tune of 10 dimensions but 11. At first, that extra dimension might seem like a trivial tweak, but it's anything but. Think of it like discovering your favorite song has a hidden verse that changes everything. Suddenly, the 5 competing versions of string theory aren't rivals, they're different angles of the same truth, unified under M-theory's umbrella. But here's where it gets mind-bending. Those 11 dimensions could give rise to an idea straight out of science fiction, the multiverse. Imagine our universe as one page in an infinite cosmic book, with other branes, short for membranes, floating like parallel sheets in higher dimensional space. These branes might collide, vibrate, or even spawn new universes in their wake. Picture two slices of bread smashing together in a higher dimensional toaster, their energy sparking a big bang. It's a dazzling vision, one that could explain why our universe seems weirdly fine-tuned for life. Maybe we're just one lucky bubble in a frothing sea of possibilities. Yet for all its elegance, M-theory has a glaring Achilles heel: proof. Unlike relativity's light-bending predictions or quantum mechanics' lab-tested precision, M-theory's ideas exist largely on chalkboards. Those extra dimensions, they're curled up tighter than a knotted string, far beyond the reach of any microscope or collider. The multiverse, by definition, other universes might be forever hidden from our view. Critics argue this pushes the boundary between science and philosophy, a theory so flexible it risks explaining everything while proving nothing. Even Nobel laureates like Richard Feynman quipped, "If it disagrees with experiment, it's wrong." But without experiments, how do we test it? For supporters, though, the math's beauty is its own clue. Just as Dirac's equations predicted antimatter before anyone saw it, M-theory's coherence might hint at truths we're not yet equipped to observe. Some suggest faint fingerprints like gravitational waves from branes colliding could one day offer evidence. Others pin hopes on quantum gravity probes or cosmic microwave anomalies. Until then, M-theory remains a breathtaking gamble, a bet that the universe's deepest secrets lie not in the particles we see, but in the hidden geometry we're only beginning to imagine. While string theory stretches the imagination with hidden dimensions, loop quantum gravity takes a radically different approach, one that asks not how to bend the rules, but where they come from in the first place. Forget tiny vibrating strings here. Spacetime itself is the star of the show, woven from an intricate network of interlocking loops. Picture the universe not as a smooth, continuous fabric, but as a shimmering tapestry of discrete threads, each carrying the smallest possible unit of space. At this level, the smooth curves of Einstein's relativity dissolve into a buzzing quantum pixelation like a cosmic pointillist painting. The key insight: gravity isn't just another force, it's the shape of reality, and loop quantum gravity treats it as fundamentally quantum. Unlike string theory's extra dimensions, this framework keeps things grounded in the four we know, but reimagines them in a startling way. Imagine zooming in on a digital photo until you see the individual pixels. Loop quantum gravity suggests spacetime behaves the same way, with gravity emerging from the spin and connections of these microscopic loops. No higher dimensions, no parallel universes, just space and time rebuilt from the quantum ground up. Leading this charge is physicist Carlo Rovelli, whose work reads like a love letter to the quantum nature of reality. In his vision, the universe's history isn't a single timeline but a web of events, where past and present blur into relational possibilities. It's a universe where time itself might not flow at the smallest scales, but emerges from these quantum handshakes between loops. The implications are staggering. Black holes could transition into white holes, and the Big Bang might not have been a singular explosion but a quantum bounce from a previous universe's collapse. But loop quantum gravity isn't without its skeptics. Without the elegance of strings or the experimental hints of supersymmetry, some argue it's more philosophy than physics. Yet its refusal to invoke unproven dimensions gives it a stark practicality, a theory that works within the universe we see rather than the one we imagine. And while it hasn't yet produced a smoking gun prediction like Hawking radiation, its math offers tantalizing glimpses, like the idea that space can't be divided infinitely, resolving the singularities that break relativity's equations. The debate between these two giants, string theory's cosmic symphony and loop quantum gravity's pixelated spacetime, isn't just academic. It's a clash of philosophies, a question of whether the universe's secrets lie in hidden dimensions or in rewriting the very concept of space. One seeks unity through expansion, the other through reduction, and in that tension we might just find the path to the theory of everything. Supersymmetry might sound like something out of a sci-fi novel, but it's one of the most tantalizing ideas in modern physics. A cosmic symmetry so elegant it could stitch the universe's forces together like threads in a tapestry. Here's the core idea: for every known particle there's a hidden twin. Electrons would have selectrons, quarks would have squarks, and even the photon would get a shadowy partner called the photino. These sparticles aren't just extras, they're the missing puzzle pieces that could balance the math of the universe. Why? Because supersymmetry smooths out the jagged edges between quantum mechanics and gravity, offering a way for all four forces to shake hands at unimaginably high energies. The beauty of SUSY, short for supersymmetry, lies in its simplicity. Picture a dance where every particle has a partner, each step perfectly mirrored. This symmetry doesn't just tidy up equations, it solves real mysteries like why the Higgs boson is so oddly light. Without SUSY, quantum fluctuation should have blown its mass up to impossible scales, like a balloon inflating to the size of a galaxy. But with sparticles cancelling out those fluctuations, the Higgs settles into the weight we observe. Even dark matter might be hiding in SUSY shadows, with the lightest sparticle, the neutralino, acting as an invisible cosmic anchor. Yet for all its promise, SUSY has a glaring problem: we haven't found it. When the Large Hadron Collider smashed protons together at near light speeds, physicists held their breath, hoping to spot a squark or photino in the debris. Instead, the collisions revealed nothing. The energy threshold for sparticles keeps climbing, like a mirage receding into the desert. Some theorists argue we just haven't looked hard enough, that SUSY particles might be heavier or sneakier than expected. Others whisper a more unsettling possibility. What if supersymmetry isn't nature's rule but a beautiful dead end? This isn't just a blow to SUSY, it's a challenge for every theory of everything candidate. String theory leans heavily on supersymmetry. Without it, those extra dimensions lose their footing. Loop quantum gravity, meanwhile, never needed SUSY to begin with, which suddenly makes its minimalist approach more appealing. The stakes couldn't be higher. If SUSY fails, it's not just one idea collapsing. It's a roadmap to unification that might need rewriting from scratch. But here's the twist: absence of evidence isn't evidence of absence. The LHC isn't done yet, and future colliders could dive deeper into energy frontiers where sparticles might still lurk. Or perhaps SUSY manifests in ways we're not even looking for, like ghosts in the quantum noise, waiting for a sharper lens. For now, supersymmetry remains suspended between hope and doubt, a theory too elegant to abandon but too elusive to confirm. And in that tension, physics presses forward, reminding us that the universe owes us no favors, only clues. Grand unified theories are like the universe's backstage crew, working quietly behind the scenes to tie together forces that seem wildly different on the surface. While string theory and loop quantum gravity grapple with gravity's elusive nature, GUTs take on a slightly more manageable challenge: uniting electromagnetism with the strong and weak nuclear forces. Think of it as merging three distinct dialects into a single language. The ambition here is staggering because at extremely high energies, like those just moments after the Big Bang, these forces might not have been separate at all. They could have been different facets of a single, primordial superforce. This idea isn't just theoretical fancy. Grand unified theories predict something extraordinary. Protons, the seemingly eternal building blocks of atoms, might not last forever. According to many GUT models, protons should eventually decay, vanishing into lighter particles over unimaginably long timescales. To test this, scientists have built detectors deep underground, far from cosmic ray interference, filled with ultra-pure water or liquid argon. They wait, watching for the faintest flash of light that would signal a proton's demise. So far, none have been caught in the act. Protons appear stable for at least 10 to the 34th years. But that doesn't mean JUTs are wrong. It might just mean protons are even more patient than we thought. Yet even if JUTs succeed in merging these three forces, they hit a wall when gravity enters the picture. Einstein's force refuses to play by the same quantum rules as the others, leaving JUTs incomplete in the quest for a true theory of everything. It's like solving 3/4 of a puzzle and realizing the last piece comes from a different box. That's why JUTs are often seen as stepping stones, necessary but not sufficient. They reveal a deeper layer of unity in the cosmos, but the final bridge to gravity remains unbuilt. The takeaway: grand unified theories show us how much closer the universe's forces are than they appear. They hint at a time when electromagnetism and nuclear forces weren't just allies but the same entity. And while they can't yet explain why apples fall or black holes warp spacetime, they push us closer to the day when all forces might finally shake hands under one universal law. Gravity is the cosmic rule-breaker, the one force that refuses to play by quantum mechanics rules. While electromagnetism and the nuclear forces neatly fit into the quantum framework, gravity stands apart, clinging stubbornly to Einstein's smooth geometric universe. The heart of the problem: quantizing gravity is like trying to build a sandcastle with waves crashing over it. Every time physicists attempt to describe gravity in the language of tiny, discrete packets, gravitons, the math collapses into infinite nonsense, a storm of uncontrollable numbers called non-renormalizability. It's as if gravity, the architect of black holes and galactic superclusters, simply laughs at our quantum toolkits. String theory offers one way out. By replacing point-like particles with wriggling strings, the infinities soften, and gravity gets a quantum passport. In this vision, the graviton emerges as just another vibration in the string orchestra, a closed loop humming with the rhythm of spacetime itself. The elegance is undeniable except for the catch. Those extra dimensions and unobservably tiny strings make the theory feel more like a mathematical mirage than testable science. Without experimental proof, string theory's graviton remains a beautiful hypothesis, floating in the realm of pen and paper physics. Loop quantum gravity takes the opposite tack. Instead of adding dimensions, it rebuilds spacetime from scratch, proposing that the universe is woven from indivisible atoms of space, tiny loops intersecting in a vast cosmic network. Here, gravity isn't a force carried by particles but a property of this pixelated geometry. Picture a digital screen, zoom in far enough and the smooth image shatters into pixels. Loop quantum gravity suggests spacetime does the same, with gravity's pull arising from the way these loops twist and link. It's a radical reimagining, one that sidesteps the infinities plaguing traditional quantum gravity. But like string theory, it struggles with validation. How do you measure spacetime's pixels when they're a billion times smaller than an atom? The tension between these approaches reflects a deeper philosophical divide. String theory seeks unity by expanding reality's ingredients, extra dimensions, supersymmetry, brains. Loop quantum gravity pares reality down to its barest quantum bones, insisting spacetime itself must be reinvented. One aims for a grand synthesis, the other for a minimalist reboot. Both paths hint at a truth, that gravity's resistance to quantization isn't a flaw but a clue, a sign that we're missing something fundamental about the fabric of existence. Until we crack this code, the theory of everything will remain just out of reach, taunting us with glimpses of a universe far stranger than we've dared to imagine. The challenge of proving a theory of everything isn't just about brilliant math, it's about confronting the brutal limits of our technology. Take the Planck scale, for instance. This is the universe's ultimate resolution limit, where space and time themselves become grainy and quantum gravity takes over. But here's the catch: reaching the energies needed to probe this scale would require a particle collider roughly the size of our galaxy. Even the most powerful machines we've built, like the Large Hadron Collider, operate at energies 1,000,000,000,000 times too low to scratch the surface. It's like trying to hear a whisper across a roaring stadium. Nature's deepest secrets are drowned out by the sheer scale of the challenge. Then there's the problem of size. Many 2E candidates, from strings to spacetime loops, operate at lengths 100 billion times smaller than a proton. To see them directly, we'd need microscopes with precision beyond anything physics can currently fathom. Imagine trying to spot a single grain of sand on the moon with a telescope from Earth. That's the level of magnification we're up against. Even indirect evidence is maddeningly elusive. Supersymmetry particles, they might be too heavy for our colliders to produce. Extra dimensions, they could be curled up so tightly that their gravitational fingerprints vanish into noise. Distance adds another layer of frustration. Some of the best clues might lie in the extreme environments of black holes or the first moments after the Big Bang, places we can't exactly visit. Cosmic microwave background radiation offers snapshots of the infant universe, but teasing out quantum gravity's faint signals from that ancient light is like trying to reconstruct a symphony from a single faded note. Yet hope isn't lost. Ambitious projects are pushing the boundaries. Future colliders, like the proposed Future Circular Collider, aim to smash particles at even higher energies, hunting for sussy particles or exotic quantum gravity effects. Gravitational wave detectors like LIGO and the upcoming LISA mission could catch ripples from cosmic strings or brains colliding in higher dimensions. And tabletop experiments are probing quantum gravity's subtle effects on everything from neutrinos to entangled particles. The takeaway: testing a theory of everything isn't just hard, it demands reinventing how we explore reality. It's a reminder that the universe doesn't owe us convenient answers, but in that struggle lies the thrill. Every dead end forces us to think creatively, every technical hurdle sparks innovation. Whether through colossal machines, space-based observatories, or quantum tricks we haven't yet imagined, the quest continues, not because it's easy, but because the rewards could redefine existence itself. What if the ultimate theory didn't just explain the universe, but rewrote what it means to understand it all? A theory of everything wouldn't merely stitch gravity to quantum mechanics. It could unravel the very fabric of how we perceive reality. Think about causality, the bedrock of science, the idea that every effect has a cause. Quantum mechanics already tosses a wrench into this, with particles that seem to decide their states upon observation. Now imagine gravity entering the quantum fray. Would spacetime itself become probabilistic, blurring the line between cause and effect? Suddenly, the past might not strictly determine the future, and the universe could feel less like a clockwork machine and more like a swirling canvas of possibilities. Then there's free will, a concept that's haunted philosophers for millennia. If a 2E describes every particle's motion with unerring precision, does that mean our choices are just illusions predetermined by equations written at the Big Bang? Or could quantum indeterminacy leave room for genuine agency, where consciousness isn't a spectator but a participant in shaping reality? The debate isn't just academic, it cuts to the core of what it means to be human. Some physicists, like Roger Penrose, suggest that quantum processes in our brains might forge a path for free will, while others insist the universe's laws leave no wiggle room. A 2E wouldn't just answer this, it could redefine the question entirely. And what about the dream of a final theory? Einstein once hoped for a universe so elegantly ordered that further inquiry would feel redundant. But history suggests otherwise. Every breakthrough, from Newton's gravity to quantum fields, has opened deeper mysteries. Even with a 2E in hand, we might face a new frontier. Why these equations and not others? What breathes fire into them, making the cosmos hum to their tune? Some argue physics could plateau, its fundamental laws fully mapped. Yet others, like string theorist Edward Witten, counter that a true 2E might reveal layers of reality so bizarre they'd make today's quantum weirdness look mundane. Perhaps the greatest revelation wouldn't be the answers, but the realization that the universe is stranger, richer, and more open-ended than we've dared to imagine. A theory of everything might not mark the end of science, but the beginning of a new chapter where the questions we ask become as profound as the answers we seek. Not everyone is convinced the theory of everything quest is worth the hype. Critics like physicist Sabine Hossenfelder argue that much of modern theoretical physics has drifted into untestable abstraction, a playground of elegant math divorced from real-world experiments. She compares some to research to medieval scholasticism, where scholars debated how many angels could dance on a pinhead, fascinating in theory but ultimately unverifiable. This tension lies at the heart of the post-empirical science debate. When theories like string theory or multiverse cosmology make predictions beyond our observational reach, how do we distinguish profound insight from intellectual fantasy? The funding dilemma sharpens these criticisms. Billions pour into particle colliders and space telescopes, while alternative approaches, like revisiting foundational assumptions, often struggle for scraps. Some argue this creates a self-perpetuating cycle. Flashy, math-heavy theories attract grants and prestige, even as their experimental prospects dwindle. The irony: Einstein's breakthroughs came from questioning Newton's absolutes, not just polishing existing frameworks. Today's physics, critics warn, risks becoming a hall of mirrors where complexity is mistaken for depth. Yet dismissing all-too-easy research as untestable overlooks key nuances. Yes, some ideas might remain speculative for decades, but so did gravitational waves, once deemed impossible to detect. The line between unverifiable today and unverifiable forever is blurrier than it seems, and while abstract math can become untethered from reality, history shows that seemingly impractical theories often sow seeds for future revolutions. Dirac's equation predicted antimatter years before its discovery. Kaluza-Klein's extra dimensions inspired string theory. The danger isn't speculation itself, but losing the feedback loop that grounds science in observation. The real challenge: balancing ambition with accountability. Physics advances when theorists dare to dream big, but also when they're forced to confront messy data. Maybe the path forward isn't abandoning grand unification, but demanding clearer signposts along the way. After all, the universe owes us no guarantees, only the thrill of the hunt, and the humility to admit when we've strayed too far from the evidence. Black holes aren't just cosmic vacuum cleaners, they're nature's ultimate physics labs, where the universe's deepest contradictions play out in real time. Picture the edge of a black hole, the event horizon, where gravity's grip is so strong that not even light can escape. But here's the twist: according to quantum mechanics, empty space isn't empty at all. It's a seething quantum foam where particle-antiparticle pairs constantly flicker in and out of existence. Normally, these pairs annihilate each other instantly. But at the event horizon, something bizarre happens. One particle falls in while its twin escapes, carrying energy away from the black hole. This is Hawking radiation, the slow leak that causes black holes to evaporate over eons. Now the plot thickens. If a black hole evaporates entirely, what happens to all the information it swallowed? A star, a spaceship, even an unlucky astronaut, all of it seemingly vanishes without a trace. But quantum mechanics insists that information can never be truly destroyed. This clash, known as the information paradox, is like a cosmic courtroom drama. On one side, general relativity claims the information is lost forever, locked behind the horizon. On the other, quantum theory demands it must be preserved, encoded in the Hawking radiation. Both can't be right, and resolving this paradox could crack open the doorway to a theory of everything. Why? Because black holes force gravity and quantum mechanics into a cage match, exposing where our current theories break down. If gravity behaves quantumly at the horizon, there must be a deeper framework that unites these laws. Some theories suggest the horizon isn't a smooth surface but a firewall of intense energy, a quantum grenade that shreds anything crossing it. Others propose holographic principles where all the information inside a black hole is somehow smeared across its surface like a cosmic zip file. Each idea is a potential clue, a breadcrumb leading toward the ultimate theory. But the real magic lies in the stakes. Black holes aren't just celestial oddities, they're time capsules from the universe's infancy, where conditions were so extreme that quantum gravity ruled. Studying them is like finding a Rosetta Stone etched with the language of the cosmos. Every photon of Hawking radiation, every ripple in spacetime from a distant merger, could carry encrypted hints about how gravity and quantum mechanics shake hands. The catch: we're piecing together this puzzle with fragments, like trying to reconstruct a symphony from a single note. Yet, with breakthroughs like gravitational wave astronomy and quantum simulations, we're inching closer. The universe has written its deepest secrets in the shadow of black holes, and we're finally learning how to read them. What if everything you see around you, the stars, the trees, even your own hands, was nothing more than a cosmic illusion? That's the mind-bending premise behind the holographic principle. An idea so radical it suggests our three-dimensional universe might actually be a projection of information encoded on a two-dimensional surface. Picture a movie screen. The images appear to have depth and movement, but every detail is secretly stored in the flat pixels of the film. The holographic principle argues reality works the same way, that the richness of our 3D world is a kind of shadow cast by data written on a distant two-dimensional boundary. This isn't just philosophical speculation. The idea emerged from the fiery heart of black hole physics, when physicists like Jacob Bekenstein and Stephen Hawking discovered that black holes have entropy, a measure of hidden information. They realized something startling. The entropy didn't scale with the black hole's volume, as you'd expect, but with the area of its event horizon. It was as if all the information swallowed by the hole was smeared across its surface like ink on a balloon, not stuffed inside. This hinted at a deeper truth. Maybe the universe, like a black hole, stores its data on a boundary we can't see. Enter string theory's most concrete holographic blueprint, the AD/CFT correspondence. Proposed by Juan Maldacena in 1997, this mathematical gem shows how a higher dimensional universe with gravity like ours can be perfectly mirrored by a lower dimensional quantum field theory without gravity. Think of it like a cosmic vending machine. Drop in equations describing particles dancing on a flat border, and out pops a fully formed universe with spacetime, black holes, and all. The implications are staggering. It suggests gravity might not be fundamental at all, but an emergent phenomenon, a side effect of quantum information shuffling on a hidden surface. Critics ask, if we're living in a hologram, where's the projector? The answer might lie in the fabric of spacetime itself. Just as a diamond's glitter emerges from billions of atoms aligning, spacetime's continuity could arise from quantum entanglement, a network of invisible connections between distant particles. Breakthroughs like quantum error correction codes even suggest how information could be redundantly stored, making the hologram resilient to glitches. Yet the hardest part is testing this. If the universe's screen exists at the Planck scale, it's far beyond our current probes. Some hope subtle anomalies in cosmic microwave background radiation or quantum gravity experiments might reveal pixelation in spacetime, tiny digital artifacts in an analog facade. Until then, the holographic principle remains a tantalizing what if, weaving together black holes, string theory, and quantum information into a narrative that could rewrite reality itself, or prove the universe's greatest magic trick. What if spacetime, the very stage on which the universe performs, wasn't fundamental at all, but a grand illusion? Imagine walking into a movie theater and seeing a breathtaking landscape on screen. The mountains seem solid, the rivers flow, but peel back the curtain and you'll find just pixels flickering in perfect sync. Some physicists argue spacetime works the same way, an emergent phenomenon rising from something deeper and stranger, the quantum entanglement of countless microscopic building blocks. This idea flips Einstein's vision on its head. Instead of spacetime bending and warping to create gravity, gravity and spacetime itself might arise from a hidden quantum reality. Think of how temperature emerges from the chaotic dance of atoms. A single molecule doesn't have a temperature. It's only when you zoom out to trillions of them that the concept even makes sense. Similarly, spacetime could be a collective effect, a kind of cosmic mirage generated by entangled qubits in a vast quantum network. The evidence look no further than black holes. When matter falls into one, it doesn't just vanish, its information gets scrambled onto the event horizon like a hologram. This suggests spacetime might be like the surface of a pond with gravity as the ripples. Dive deeper and the water dissolves into individual molecules. Likewise, spacetime's smooth geometry could dissolve into a web of quantum connections. Experiments with quantum computers already hint at this, showing how entangled qubits can mimic spacetime's structure, bending and warping in simulations like a digital universe in miniature. But the real kicker, if spacetime emerges, so might causality, the very notion of cause and effect. In this view, time isn't a flowing river but a tapestry of relationships where before and after are just patterns in the quantum weave. It's a vision so radical it makes string theory's extra dimensions seem tame. And while we can't yet peer behind the cosmic curtain, the hunt for quantum gravity's fingerprints in particle collisions, gravitational waves, or even tabletop experiments could one day reveal the secret code stitching reality together. The takeaway: the universe might not just be stranger than we imagine, it could be stranger than we can imagine, built not on space and time, but on something far more mysterious. Mathematics has always been the silent architect of physics, the invisible scaffolding holding up our understanding of the cosmos. But here's the haunting question: are we uncovering universal truth written in numbers, or are we inventing tools to carve sense from chaos? Take the Dirac equation, a piece of mathematical poetry scribbled down in 1928. At first glance, it was just a way to reconcile quantum mechanics with Einstein's relativity. But buried in its elegant symmetry was something shocking: a prediction of antimatter, a mirror world of particles no one had ever seen. When the positron was discovered 4 years later, it wasn't just a triumph of prediction. It was a moment where math seemed to whisper secrets about reality itself. This eerie precision fuels debates that split physicists down the middle. On one side, thinkers like Max Tegmark argue the universe is mathematics, that every galaxy, every atom, even consciousness itself, is just a structure in an abstract mathematical space. In his mathematical universe hypothesis, there's no distinction between the equations and the reality they describe. The cosmos doesn't follow mathematical laws, it is those laws playing out in an infinite tapestry of numbers. It's a radical vision, one where pi isn't just a ratio but a fundamental feature of existence, as intrinsic as gravity. Yet others push back. If math is discovered, why do some frameworks like Euclidean versus non-Euclidean geometry feel like choices, not revelations? When Einstein needed curved spacetime for general relativity, he didn't find the math waiting neatly on a shelf. He borrowed from Riemann's then obscure geometry, a tool crafted decades earlier with no inkling of its cosmic role. This suggests math might be more like a language, invented by humans but uncannily good at describing nature's patterns. The tension here isn't just academic. It shapes how we hunt for a theory of everything. If math is the universe's native tongue, then uncovering its deepest symmetries, like the Lie groups that underpin particle physics, could be our Rosetta Stone. But if math is a lens we've polished over centuries, maybe the 2E will demand something entirely new, a formalism we haven't yet imagined, one that bends or breaks today's notation. Either way, the track record is hard to ignore. From Fibonacci sequences in sunflowers to the Higgs boson's mass-matching predictions to 12 decimal places, math's predictive power borders on the supernatural. Whether it's discovery or invention, one thing's certain: in the quest to unify physics, numbers aren't just the map, they might be the territory. Could artificial intelligence be the missing partner in humanity's greatest intellectual quest? While physicists grapple with abstract equations and elusive particles, machine learning is quietly reshaping how we search for a theory of everything, turning vast datasets and complex simulations into pathways where human intuition might never tread. Take string theory's notorious landscape problem. With potential solutions numbering 10 to the 500 power, more configurations than atoms in the observable universe, finding viable compactifications of extra dimensions seemed hopeless. But when researchers at Google's DeepMind trained neural networks on this cosmic haystack, something remarkable happened. The AI began identifying stable configurations human theorists had overlooked, spotting subtle geometric patterns across millions of possibilities in days rather than decades. It didn't understand the physics in our sense, but it revealed connections our pattern-seeking brains couldn't see. This synergy between silicon and scientist goes beyond brute force computation. At MIT, AI systems are being taught the very language of physics, ingesting centuries of equations to propose new mathematical structures that could bridge quantum mechanics and gravity. Picture a system that reads every physics paper ever written, not just for citations, but for hidden symmetries and untested mathematical bridges between theories. Some algorithms already suggest novel quantum field theories or spot inconsistencies in existing models, serving as digital colleagues that never tire of tedious calculations. Yet the real revolution might be in how AI handles what humans struggle with most: radical paradigm shifts. When DeepMind's AlphaZero mastered chess, it abandoned centuries of opening theory for strategies that initially looked nonsensical to grandmasters until they won. Similarly, an AI exploring the 2E might suggest frameworks that seem alien at first glance, like an architect designing buildings in 5 dimensions when we've only ever seen 3. The challenge: teaching these systems the difference between mathematical elegance and physical plausibility, a nuance that separates beautiful equations from testable reality. Projects like Princeton's AI Feynman show glimpses of this future. Named after the legendary physicist, the algorithm distills complex data into simple laws, having already rediscovered classic physics equations from scratch. Now imagine scaling this up to quantum gravity's uncharted territory. The dream isn't just automation, it's collaboration, where human creativity and machine perception combine to crack codes the universe has kept hidden for 14 billion years. The theory of everything might not be written in human handwriting alone. A verified theory of everything wouldn't just rewrite physics textbooks, it would ripple through every corner of human culture, reshaping how we think, create, and innovate. Picture the Copernican revolution, which didn't merely move Earth from the center of the cosmos, it shattered humanity's cosmic ego, inspiring everything from Galileo's defiance to the existential musings of modern literature. Now imagine a 2E delivering a similar shock, revealing that space-time, matter, and even causality are threads in a deeper tapestry. Artists might grapple with this new reality through surreal installations where dimensions twist into impossible shapes, while filmmakers could visualize quantum gravity's paradoxes in ways that make Inception look straightforward. Technologically, the impact could dwarf even the quantum computing revolution. If a 2E exposes hidden layers of reality, extra dimensions, quantum foam, or emergent spacetime, engineers might harness phenomena we can't yet dream of. Materials science could leap forward by exploiting unified force interactions, creating superconductors that work at room temperature or alloys with programmable gravity responses. Imagine cities built with metamaterials that bend spacetime itself, rendering buildings earthquake-proof by distributing stress across dimensional folds. And what if we cracked gravity's quantum code? Suddenly, propulsion systems that manipulate spacetime, like Alcubierre's theoretical warp drive, could shift from sci-fi to blueprints. Philosophy would face its greatest upheaval since Nietzsche declared God is dead. A2E could upend debates about free will, consciousness, and even the nature of existence. If the universe's fundamental layer is pure information, as holographic principles suggest, does that make reality a simulation or something stranger? Religions might reinterpret creation myths through the lens of quantum genesis, while ethicists wrestle with technologies that could literally rewrite the fabric of space. Even pop culture would transform. Video games might feature physics engines where players manipulate fundamental forces, while musicians compose symphonies based on the vibrational frequencies of cosmic strings. The A2E's cultural footprint could mirror how quantum mechanics birthed the transistor, but this time the ripple effect wouldn't just change how we live. It would redefine what it means to be human in a universe far wilder than we ever dared to imagine. History has a sobering lesson for us. Every leap in understanding the universe has come with unintended consequences. The discovery of nuclear fission unlocked both clean energy and the atom bomb, splitting humanity's future into paths of hope and horror. If a theory of everything hands us the keys to spacetime itself, who gets to decide how those keys are used? The power to manipulate fundamental forces wouldn't just be another tool in our toolbox, it could redefine power itself. Picture a world where gravity is no longer a constant, where matter can be rewritten at the quantum level. The same equations that explain the birth of stars might also blueprint technologies capable of collapsing them. This isn't abstract paranoia. Robert Oppenheimer's haunting words after the Trinity test, "Now I am become death, the destroyer of worlds," weren't just poetic regret. They were a warning about the moral weight of knowledge. A2E could dwarf even nuclear physics in its potential for disruption. Imagine a society where the wealthy could distort spacetime for private wormhole travel, or militaries weaponize singularities. The gap between haves and have-nots wouldn't just be economic, it could become cosmic. Yet the dilemma runs deeper than access. Some truths might be inherently destabilizing. What if A2E reveals that reality is inherently unstable, or that certain experiments risk unraveling spacetime's fabric? Physicists already debate whether high-energy colliders could create miniature black holes, a scenario once dismissed as sci-fi but now taken seriously in peer-reviewed journals. The Large Hadron Collider's safety assessments included years of debate, and that was just for probing the Higgs field. A2E might expose risks we can't yet fathom, forcing a terrible choice: suppress the knowledge or risk catastrophe. The question isn't just scientific, it's about who gets a seat at the table. Should a breakthrough of this magnitude be governed by academic institutions, international treaties, or some new ethical framework? The Manhattan Project was shrouded in secrecy, but A2E's implications are too vast for backroom decisions. Crowdsourcing wisdom sounds ideal until you consider bad actors. Open source the math and you might democratize discovery, or hand apocalyptic tools to dictators or terrorists. Perhaps the greatest irony is that a theory seeking unity could divide us more than ever. But there's another path: learning from past mistakes. The nuclear age gave us non-proliferation treaties and the Pugwash conferences, where scientists advocated for restraint. A2E might demand something even bolder: a global covenant on fundamental physics, where transparency and accountability aren't afterthoughts but prerequisites. After all, the universe's deepest truth shouldn't be guarded like state secrets, but they can't be left unguarded either. The lesson isn't to fear knowledge, but to respect its weight. Because understanding everything means responsibility for everything. While string theory and loop quantum gravity dominate the unification debate, a handful of radical outsiders are rewriting the rules entirely, not by adding dimensions or quantizing space, but by questioning whether physics has been speaking the wrong language all along. Take Stephen Wolfram's physics project, a moonshot attempt to rebuild the universe from simple computational rules. Forget elegant equations. Wolfram proposes that reality might emerge from hypergraph rewriting systems, where space and time are just patterns in a vast cosmic computation. Picture the universe as a cellular automaton on an unimaginable scale, with every collision, every galaxy, even your thoughts right now, unfolding from discrete steps in an underlying program. It's a vision where physics becomes less about solving equations and more about debugging nature's source code. Then there's causal dynamical triangulation, or CDT, a theory that treats spacetime like a Lego set. Instead of smooth curves or vibrating strings, CDT builds the universe from tiny, four-dimensional triangular blocks glued together in specific causal sequences. These blocks don't just approximate spacetime, they are spacetime with gravity emerging naturally from how they connect. The magic happens when you simulate these triangulations at scale. Under the right conditions, a four-dimensional universe bubbles out of the chaos, complete with relativistic effects and quantum fluctuations. It's as if you gave a child triangles and they accidentally built general relativity. What makes these fringe ideas so compelling isn't just their audacity, it's their willingness to jettison sacred assumptions. Wolfram's project challenges the notion that fundamental physics must be expressed in continuous equations, while CDT abandons smooth spacetime entirely. Both suggest that the universe's deepest truths might not live in the language of calculus or geometry, but in the logic of networks and algorithms. Of course, the establishment raises eyebrows. Without experimental validation, critics dismiss them as mathematical fan fiction, beautiful constructions with no anchor in reality, yet history favors the heretics. When Einstein reimagined gravity as geometry, or when Dirac conjured antimatter from a minus sign in an equation, they too were outliers. The lesson: every paradigm shift begins as a fringe idea. Whether Wolfram's hypergraphs or CDT's spacetime Lego ever prove correct, they're expanding the toolbox of possibility, reminding us that the path to a theory of everything might not be a straight line but a wild, branching exploration of every possible way the cosmos could make sense. Ever heard someone joke that a theory of everything will finally tell us why your Wi-Fi cuts out during storms? The hype around unifying physics has spun up some wild misconceptions, myths so sticky they've practically become urban legends. Let's bust a few. First up, the idea that a 2E will suddenly explain everything, not just gravity and quantum weirdness, but consciousness, love, even why your cat ignores you. Spoiler, it won't. A theory of everything aims to unite the fundamental forces, not decode your dreams. Think of it like assembling a car engine. You're figuring out how the pistons and crankshaft interact, not why your uncle insists on blasting polka music while driving. Then there's the fear that nailing down a 2E will solve physics, leaving scientists twiddling their thumbs in boredom. Cue the memes of physicists weeping over their now useless chalkboards. But here's the reality: every breakthrough in history has opened more doors than it closed. Newton's laws didn't end physics, they launched centuries of discovery. A 2E would be less of a finale and more of a backstage pass to even crazier questions, like what lurks beyond space-time or whether multiple universes are juggling different rulebooks. Another gem, that a 2E will be one sleek equation you can tattoo on your arm. Sure, E equals mc squared is chic, but unifying gravity with quantum mechanics might look more like a sprawling wiki of interlinked principles. Even Einstein's unfinished unified field theory filled notebooks with tensors that'd make a supercomputer sweat. The universe doesn't owe us simplicity, just ask anyone who's tried filing taxes. And let's not forget the conspiracy-adjacent myth that physicists are intentionally making this stuff convoluted to seem smarter. Trust me, if there were a shortcut, they'd take it. The math is hairy because reality is stranger than fiction. You try describing a black hole's interior without bending a few brain cells, the takeaway. A theory of everything won't hand you life's meaning on a cheat sheet, but it might rewrite how we see existence itself. And hey, if it does explain your cat's behavior, physicists will be as surprised as you are. Brian Greene's voice carries a quiet intensity when he describes string theory's promise. Think of the universe as a grand symphony, he might say. Each vibration of these tiny strings, each note corresponds to a particle, a force, even spacetime itself. The mathematics isn't just elegant, it's inescapable. When you see how gravity and quantum mechanics slot together in higher dimensions, it's like witnessing a cosmic puzzle clicking into place. He'd acknowledge the criticisms, the lack of experimental proof, the dizzying landscape of possibilities, but his conviction wouldn't waver. Every revolutionary theory starts as a sketch. Einstein's relativity was pure math for years before Eddington saw starlight bend. The universe doesn't reveal its secrets on demand. Lee Smolin, on the other hand, leans forward with the urgency of a detective chasing a lead. Loop quantum gravity isn't about adding fancy new ingredients. It's about taking spacetime apart to see what it's really made of, he'd argue. Why invent 10 dimensions when the problem might be right here in the quantum structure of our familiar four? His hands might sketch the air, drawing the interwoven loops that replace smooth geometry with a dynamic network. We've seen this play before, Newton's absolute space, the luminiferous ether. Sometimes the answer isn't more, but deeper. The frustration with string theory's dominance would simmer beneath his words. Science advances when we follow the evidence, not just the prettiest equations. The tension between these perspectives isn't personal, it's philosophical. Greene's universe hums with hidden harmonies. Smolin's is a quantum construction site. Yet both share a rare humility. If tomorrow's experiment points to brains or spin networks, I'll follow the data, Greene admits. Smolin nods agreement. The worst thing we could do is cling to dogma. Nature's under no obligation to fit our notebooks. Behind their debate, younger voices add texture. A postdoc working on emergent spacetime might muse, what if both camps are seeing fragments of the same elephant? Strings could be vibrations of the loops, not rivals to them. A veteran experimentalist weary of theory wars would likely chuckle. I don't care if gravity's made of strings, loops, or pixie dust, just tell me what to look for in my detector. The takeaway: physics thrives on this friction. Every "but what if" pushes the field closer to truth, especially when the answers aren't tidy. As Greene once quipped, the universe isn't here to make sense to us, but that won't stop us from trying. The hunt for a theory of everything won't end with chalkboard equations. It'll be forged in the fire of next-generation experiments and cosmic observations. Picture the Future Circular Collider, a proposed particle accelerator with a ring 16 miles longer than the Large Hadron Colliders, capable of smashing protons at energies 8 times higher. If built, this behemoth could peer deeper into quantum foam than ever before, hunting not just for supersymmetry's particles but for faint echoes of extra dimensions or microscopic black holes evaporating in a flash of Hawking radiation. Even a null result would be seismic, forcing physicists to abandon cherished theories or dream up wilder ones, but colliders alone won't crack the code. Space telescopes like the upcoming Laser Interferometer Space Antenna, or LISA, will listen for gravitational waves from collisions between supermassive black holes, events so cataclysmic they might warp spacetime itself in ways that reveal quantum gravity's fingerprints. Meanwhile, the James Webb Space Telescope's successors could analyze the cosmic microwave background for irregularities hinting at primordial quantum fluctuations, or even collisions between our universe and a neighboring brain in the multiverse. Then there's the quiet revolution in quantum simulation. Labs are already creating analog black holes using Bose-Einstein condensates, ultra-cold atoms that mimic event horizons, or studying entanglement in diamond defects to probe how spacetime might emerge from quantum links. These tabletop experiments won't replicate the Big Bang, but they could uncover universal behaviors shared by all quantum gravity models, like how information escapes a black hole or why spacetime appears smooth at large scales. Yet the biggest breakthroughs might come from math itself. Just as Einstein needed Riemann's geometry to describe curved spacetime, new mathematical languages, perhaps inspired by machine learning, discovered patterns or exotic algebraic structures, could provide the scaffolding for unification. Young theorists are already exploring non-commutative geometry, where coordinates defy traditional algebra, or topological quantum field theories that treat particles as knots in spacetime. The timeline: optimists whisper decades, realists say centuries, but history shows scientific revolutions thrive on patience. Maxwell unified electricity and magnetism in 1865, but radio waves weren't detected until 20 years later by accident. The theory of everything may demand not just brighter minds, but new ways of thinking altogether. And that's the thrilling part. The final answer might be waiting in a notebook somewhere, scribbled by a student who hasn't even been born yet. So where does this leave us in humanity's grand quest to unify physics? We've soared through the labyrinth of string theory, where tiny vibrating strings hum the universe's symphony in hidden dimensions. We've trekked across loop quantum gravity's pixelated spacetime, where reality is stitched together by interwoven threads of quantum fabric. We've glimpsed supersymmetry's elegant mirror world, where every particle has a hidden twin, and marveled at the holographic principle's audacious claim that our three-dimensional reality might just be a cosmic projection. Each of these frameworks dazzles with its own brilliance, its own flashes of insight, yet none has fully cracked the code. The challenges loom large, extra dimensions curled too tightly to see, particles too elusive to catch, math so complex it defies even our most powerful supercomputers. But here's the thing: this isn't a story of failure. Every dead end has illuminated new paths. Every failed experiment, like the hunt for supersymmetry at the Large Hadron Collider, has sharpened our questions. Theories once dismissed as fringe, like emergent spacetime or causal dynamical triangulation, are now gaining traction, reminding us that breakthroughs often come from the margins. The very struggle to reconcile quantum mechanics and relativity has birthed entirely new fields of thought, from quantum information science to topological phases of matter. Even without a final answer, the journey has already reshaped our understanding of reality. And let's not forget the most exhilarating possibility of all: that the ultimate theory might still be out there, waiting in some uncharted corner of mathematics or physics, ready to rewrite the textbooks. Maybe it's a fusion of existing ideas, or something so radical it hasn't even been dreamt up yet. The greatest discoveries often come when someone dares to ask a question no one else thought to pose. That someone could be you, yes, you, watching this right now. The next Einstein or Noether might be scribbling equations in a notebook, or tinkering with code in a garage lab, or simply staring at the stars and wondering, what if? So tell me, which of these theories sparks your imagination? Is it the cosmic hologram, the vibrating strings, the quantum loops, or do you have a wild idea of your own? Drop it in the comments below. The search for the theory of everything isn't just for physicists in ivory towers. It's for anyone who's ever looked up at the night sky and felt that tug of curiosity. Because the universe's greatest secret, it's out there, whispering to whoever's willing to listen, and who knows, maybe the next leap forward will start with you.